Good afternoon, and welcome to this talk is Behind the Scenes of iOS and Mac Security. This is South Pacific, and our speaker is Ivan Krstić. So if that means a lot to you, you're in the right place. So thank you very much. Just a few little notes before we begin. So stop by the business hall located in Mandalay Bay, Oceanside and Shoreline ballrooms on level 2. The Black Hat Arsenal is in the business hall on level 2. Lunches in Bayside AB from 1 till 2:30. And don't forget the merchandise store on level 2 and session recordings from SOK. They have a desk on every level. Just as a final reminder, please make sure your cell phones are on vibrate. It's way nicer for everybody else. But without further ado, let's get started. And please join me in giving our speaker a warm welcome, Ivan Krstić.
Thank you. Thanks, folks. It's great to be here. My name is Ivan. I run SEER, Security Engineering and Architecture. This is the group at Apple that's end-to-end responsible for the security of everything that we ship to our users. We have a lot to cover today, so we're going to just jump right into it and start talking about Mac Secure Boot. We have been investing heavily into macOS security. Some things that you may have noticed are things like Gatekeeper and user privacy protection, which are features that we pioneered in macOS Mojave and continue to improve in Catalina. So in Catalina, Gatekeeper is getting vastly expanded. There will be malware checks in virtually every execution path. Software has to be notarized to run. And then user data protections, which we introduced with Mojave, was a way of forcing apps to require user consent before being able to access highly sensitive user data like these categories. Anytime an app tried to do this and not use traditional API, it would pop a dialog like this. In Catalina, we went and added many more areas to be covered by this protection. So we've been investing heavily in this, but these are all features that are visible to the user. And what about things that are lower in the stack? What about Secure Boot? We have an incredibly powerful Secure Boot implementation in iOS. It's battle hardened. It's been running for 11 years, and we think it's state of the art. But what that means is that we have a very clear picture of the kind of security requirements that we would place on a Mac Secure Boot implementation. And when we looked at the way Secure Boot tends to work on x86 systems, traditionally it's done with UEFI Secure Boot, we found that it doesn't meet almost any of our security requirements for macOS Secure Boot. So what we decided to do instead is build our Mac Secure Boot on top of the T2 security chip. This is our second generation custom silicon for the Mac dedicated to security. It brings a secure enclave coprocessor with it. And the way our Secure Boot now works is that T2 is actually what initializes boot before passing over to x86. So if we break that down, when power comes online, the T2 ROM runs and continues to cryptographically verify every subsequent step of boot, terminating with UEFI firmware, which is still verified on the T2 side before being moved over to x86 and executed, where it will continue to check the remaining pieces of boot, finally culminating in macOS running. Now, it turns out that there are some critical challenges with bringing a powerful Secure Boot implementation to Mac that don't exist on iOS. Most importantly, direct memory access attacks that are possible from physical accessories, which can basically read and write host memory without any involvement from the CPU, as well as an architectural feature of PCIe, which is called option ROMs or OROMs, which are device-specific drivers for the early boot environment. So I want to walk you through what we had to do to be able to contend with these challenges. Before that, a very quick refresher. This is Operating Systems 101, how page tables work. So this is a CPU running in normal 64-bit protected mode. It's asking to read some memory from a virtual address. That goes to the MMU, which actually turns around, consults page tables, determines that this virtual address corresponds to a specific physical address in memory, and that is the data that gets returned. This is important because it'll be the basis of many of the systems that I'll be discussing with you in a moment. So I mentioned DMA. The reason this exists is because certain kinds of accessories have to be able to do very high throughput transfers. If you're talking about storage or graphics or network cards, you really want them to be able to move data into RAM without having to go through the normal CPU path. But what that means is, in the good case, a network interface card can take a network packet that came in and DMA it directly into a packet buffer that's been allocated on the kernel heap. In the bad case, the same device could take malicious code and simply place it over the running kernel, completely taking over execution of the system. So Intel introduced a technology called VTD, which is a way to initialize an input-output memory management unit to manage these kind of DMA transfers. And we have used this technology to protect the kernel since OS X Mountain Lion in 2012. So here's the premise with VTD. Our VTD packet buffer here would say, look, only the packet buffer is writable by the accessory for DMA. Everything else is simply not mapped, which means that the network packet could never go and overwrite the macOS kernel. So before VTD was introduced, you were able to plug in a malicious Thunderbolt accessory while macOS kernel was running, and you could simply go and do the malicious DMA and take over execution of the system. When, in 2012, we shipped VTD, by setting up VTD early enough before Thunderbolt accessories could be used, we simply prevented this attack, because by the time you could plug in a Thunderbolt accessory, it was contained with VTD and it could no longer do malicious DMA. But there's an obvious question here. What if you plug in the malicious accessory earlier? Specifically, what if you plug it in before macOS is even running? It turns out that VTD was originally really intended for operating systems, and it wasn't until 2015 that Intel published a paper showing how VTD could be used inside the UEFI firmware environment. We implemented this and we shipped it in 2016, which meant essentially taking this architectural lift of moving VTD setup from macOS side to much earlier during UEFI initialization and before malicious accessories could be connected. That solved that problem, but it turns out that PCIe devices are initialized even earlier during firmware boot. And so the way to address this is once again picking up the VTD setup and making sure it can take place before a single PCIe device is initialized and is therefore able to do malicious DMA. We deployed this protection as well. But it turns out there's one interesting piece of this still left. We talk about UEFI firmware as this monolithic box. And what actually ends up happening is that UEFI firmware boot has two stages. There's the stage that we think of as normal UEFI firmware, and this is where we now have VTD set up and we have all the protections we want. But there's a portion of UEFI that executes before RAM is available. This is our pre-RAM firmware. And during that execution, PCIe bus 0 devices, which are these hyper-privileged hardware devices like SATA controllers, XHCI controllers, the management engine, they are all initialized. And by virtue of being initialized at this point in the boot process, they are able to execute malicious DMA immediately. So the answer feels pretty straightforward. We could pick up VTD setup and we could somehow move it before PCIe bus 0 devices are initialized. But there's a catch. VTD relies on an IOMMU being configured. You configure an IOMMU by pointing it at page tables, and page tables have to live in RAM. But RAM is not up yet. Here's what this actually looks like. This is the moment before RAM is up and running. You'll see in the lower right-hand corner that it's not initialized yet. And there's a moment where execution transfers. RAM is just coming online. The moment RAM comes online, we're going to try and take the UEFI firmware from the T2 side and copy it into running RAM. But at this exact moment, we have placed the firmware there. We have not yet even begun executing a single instruction. And of course, VTD is not configured, which means that a malicious PCIe bus 0 device can strike right now while this firmware code is in memory but hasn't run yet and replace it with malicious code, completely taking over the system. So what do you do in a situation like this? How do you deploy VTD when you can't put a page table in RAM? Well, here's the answer. You initialize a table full of zeros. And you say, that's going to be our root table, and we're going to use it for VTD as well as for interrupt remapping. And if you take our firmware and take a look at some of the bytes in it, you find this interesting section that is really just all zeros. But it turns out that all of these zeros are a compiled page table that we were able to place into our UEFI firmware binary. This means that we can, during initialization, before RAM is up, point VTD at what looks like a page table, but again, is really just a bunch of bytes mapped in the processor cache out of our firmware binary. What this gives us is the following property. The moment the UEFI firmware moves into x86 RAM when RAM has finally come online, VTD is already up and running. And if a malicious PCIe bus 0 device attempts to actually go and override that firmware, the VTD will consult page tables. Again, that's our set of zeros, which translates to deny everything, and the transfer will be denied. So in this way, we're able to do VTD setup before PCIe bus 0 is capable of doing any malicious DMA. I also mentioned option ROMs. Option ROMs are interesting. They're an architectural property of PCIe, and the way to think about it is maybe you're booting your system from something like an external RAID controller. Your boot firmware doesn't know how to talk to the RAID controller, and therefore it couldn't boot from it. So PCIe provides this ability for this external accessory to say, hey, boot environment, I have a driver. Here it is. Run it, and you'll know how to talk to me. Unfortunately, that option ROM runs in ring 0 along with the rest of all of UEFI, which means that any code that runs after the SOROM runs, including the booter and the kernel, could be completely compromised by an overwrite. So here's essentially what this looks like. You'll see that everything is in ring 0, sharing one virtual memory space. That means that every one of these option ROMs can go and directly write over core UEFI firmware if necessary. What we want to do here is first pull out all the option ROMs and put them in ring 3, which is substantially less privileged. But we want to go one step further and give them each their own virtual memory space. Finally, we want to initialize our option ROM sandbox driver, which is going to mediate what these option ROMs are actually capable of doing. So one option ROM trying to interfere with another or trying to interfere with direct core UEFI firmware would simply be denied by the sandbox driver. The premise here is that the option ROM sandbox can limit both what OROMs can call and which interfaces they can install, what they can publish. And we can do this in a way where normal option ROMs that are benign, that are actually trying to help accessories be used, continue to work without any issue. But an option ROM that tries to say, for example, allow me to write to the NVRAM interface, which stores security configuration, would simply be denied by the option ROM sandbox. Meanwhile, the first two option ROMs that are just saying, I'm a driver for the piece of hardware I came with, are allowed through. The third one, continuing to try to misbehave, says, I'm a secure boot driver. That's what I'm trying to publish. The option ROM sandbox is going to block this as well. The easiest way to think about this is that the first thing the option ROM sandbox does is restrict the option ROM to only be able to talk to the device in its sandbox, which is the device that the option ROM came with. And this VTD policy continues to allow DMA between the device and its option ROM, preserving the high throughput property that we wanted from DMA, and the OROM doesn't even have to be VTD aware. So I want to show you what this looks like very quickly. Can we switch to demo, please? OK. What I have here is the Intel Symix full system simulation environment. And I've booted it to a point where we are simulating that a malicious accessory is plugged in and has a malicious option ROM. So you can see the entries at the bottom left. This is where our option ROM started to run. It located that it has access to 568 handles in the UEFI environment and close to 1,500 published protocols. It was able to go through them and locate the one for Apple Secure Boot and find its address. And the interesting thing here is that if we look at the current protection level, you'll see that this malware, where we have a breakpoint, is running in ring 0. So if we now continue booting, the malware will proceed and find our target function. The target function in this case is the firmware password screen and the function that validates whether the correct firmware password was entered. So let me show you what that looks like as well. If I disassemble at that address that the malware found, you see basically a call to the function that will validate the password. It'll make sure that 0 is reached, 0 is success, and if it's not, it's going to jump elsewhere and say the password was not correct. But if I let the malware continue to run, it'll go and modify its target. And if we now disassemble the very same address, you'll see that this was completely patched out and replaced with something that will allow any password to go through. Indeed, if we continue execution, this is our malware firmware password screen. That's our hacker Mallory wearing a black hat. And I can type any password into the screen, and boot will continue as if I supplied the correct password. We're going to bring up Symix now in a different configuration. We're going to say, Same situation, but in a piece of UEFI that is running our option around sandbox. We expect a pretty different situation here. For one thing, we expect the current protection level to be different. We also expect that simply the number of interfaces that will be published and available to the malware is substantially different than what we saw before. And indeed, here we are. The malware is now running. If I look at the current protection level, we are no longer in ring 0. We are deprivileged in ring 3. You'll notice that the malware tried to enumerate every handle and protocol available and found 3 and 6, down from nearly 500 and 1,500, which is just a massive attack surface area reduction. And finally, when it tried to find the Apple Secure Boot protocol in order to try and patch it, it just couldn't find it. When it then tried to blindly patch something, it took a page fault and simply couldn't do anything. We're now at the real firmware screen. It was not able to patch any of that. And if I try an arbitrary password in this screen, it's simply rejected. Thank you. Back to the main machine. Of course, what option around sandbox means is that attackers will be driven now to privilege escalation attacks and sandbox escapes. So we didn't stop here. We added a strong set of exploit mitigations to EFI on T2 systems. That's everything from stack cookies, SMAP, SMEP, and even suspector and meltdown mitigations. In short, the T2 security chip let us take some key secure boot properties from our iOS secure boot, bring them to the Mac, and far outclass UEFI secure boot-based systems. We also built DMA protections for PCIe Bus 0, which are state-of-the-art protection against DMA attacks targeting firmware. In fact, we are the first company to do this, as well as the macro ROM sandbox, which provides a new and novel defense against malicious option ROMs. Here, again, we were the first to build a system like this. I want to switch gears and talk about iOS code integrity protection. iOS has always had code integrity protection since day one, both for userland and for kernel. But before iOS 9, this was a software-only protection. The check was done only at boot, and a single kernel write gadget was able to fully disable the system. So with iOS 9, we said we wanted to take a harder look at a stronger kernel integrity protection mechanism. And we specifically wanted to build something that could live within the harshest threat model we could imagine, with arbitrary kernel read-write, arbitrary instruction pointer control, and arbitrary read-write via DMA. So V0 was our software-only prototype. And the way it worked is by creating a secure EL3 monitor that would create an array of kernel page tables and text hashes. Periodically, it would verify them. It would panic if there was a mismatch. And as we expected, this was effective against long-lived patches, but a monitor like this is inherently vulnerable to races, which we knew. So here's just what that monitor looks like. You can see the monitor code collecting all the hashes on the right. And that's a fairly straightforward EL3 implementation. What's interesting about this use of EL3 is that it's pretty unusual. EL3 does not get direct access to userland or kernel page tables. So what we have to do instead is use the fact that EL3 has access to floating point instructions and interrupts to force the kernel to periodically trap into the monitor, letting us go and do these checks. This was an interesting prototype, but we learned some pretty immediate tactical lessons from this, which is, as we knew, inherently vulnerable to races. It's not enough to just protect code. We also have to protect a bunch of critical data regions. And it would be much easier to build a hardware architecture that actually supports our security requirements than trying to do this in the other direction. So with iPhone 7, we introduced kernel integrity protection v1. And this was the first time that we built new hardware specifically tailored to our goals. We had 3 key requirements for our threat model that we wanted to be met in hardware. The CPU would not allow any modification of kernel memory. It would prevent any EL1 execution of non-kernel memory. And the memory controller would prevent DMA writes to the protected physical range. So this is what that looks like. And the important thing to realize about this is the MMU here is overriding page tables when it comes to how the kernel is mapped. In other words, the MMU will make it so that the kernel is only ever read-only, even if page tables say that it's in fact read and write. This gave us a very strong design for code, but it turned out that protecting data required quite a bit of additional finesse. Neither kernel integrity protection v0 nor v1, which I just showed you, do anything to prevent modification of TTBR1. This is the register that tells the CPU where to actually find the kernel's page tables. And so in KIP v1, to protect against an attack on TTBR1, we had to set up a very, very careful initialization sequence that makes sure that by the time the CPU is done initializing, there remain no instructions that could be used by an attacker to modify TTBR1. We were able to do that, but it required a pretty substantial rework of our kernel cache layout. It also required build time checks that no TTBR1 write gadget was inadvertently introduced into the kernel cache. The upside, though, is that it was very effective at protecting kernel code integrity. There was only one known public bypass ever, and it was a simple off-by-one error in a protection range calculation, which we immediately addressed. With iPhone XS, we decided to go further. We took all the lessons from KIP v1 and applied them to the next version of kernel integrity protection. The key idea here is to vastly simplify the design and get something that is much more secure as a result. So all the control bits that would allow changes to things like TTBR1 or DMMU are now guaranteed in the hardware as unmodifiable. And this replaces our complicated initialization instructions from KIP v1. Another thing we did in KIP v2 is we vastly simplified the interaction with power management. Power management transitions frequently introduce brittleness or fragility into security properties. And here, KIP v2 simply preserved kernel integrity protection configuration across power management transitions. In summary, we gained robust enforcement of kernel code and read-only data integrity with a hardware implementation that is tailored to software security requirements. And this is something that only Apple can do because we control the silicon and we control the software. And this feature ended up being a pretty critical foundation for the next generation of our security features. One thing we learned when building KIP is that we could benefit from another kind of CPU primitive. This is something we call fast permission restrictions, or APRR, and it's shipped in iPhone X. The way to think about this is it's a CPU register to very quickly take a piece of memory that is RWX and restrict it to a more restrictive configuration per thread. By doing it this way with a processor register, we don't have to take a syscall, we don't have to take the time to walk page tables and flush them just to change permissions, which is a really substantial performance improvement. So here's what this looks like in practice. Before APRR existed, this is a memory diagram of a process that relies on the JavaScript core JIT, and you'll see that the JIT memory is mapped read, write, and execute. With APRR, what we do is only for JavaScript core execution threads do we set a non-write APRR mask, which means that those threads have effectively only read and execute access to the region, whereas, of course, the JIT compiler sets a no execute mask, giving it read and write. So that's great, but what about protecting userland code integrity? KIP gives us a very strong mechanism for kernel text, but it does this with the MMU relying on being able to override page tables because kernel code is static. Userland code is not static, it's dynamically loaded. We would somehow need some kind of dynamic override. So with iPhone XS, we introduced the page protection layer, or PPL. It ensures that userland code cannot be modified after a signature check completes. It builds on top of the other hardware mechanisms we've built before, and it basically hoists management of page tables and code signing validation into a very, very small trusted computing base that is tightly audited. It guarantees that only code running within the page protection layer can actually alter these protected pages. So this is pretty interesting. Here's what it does. It takes kernel code and basically splits it into two worlds. PPL code, as well as its heap and data page tables, are simply not writable during normal execution. In fact, PPL code is not even executable. It's read-only. Then we have the special pair of trampolines that can be used to transition into PPL mode, but in a very carefully controlled fashion. That trampoline, for example, prevents a ROP attack from entering PPL. Once we enter PPL mode through the trampoline, which verifies that the trampoline fully completed executing, we suddenly flip our PPL data and page tables using APRR to be both readable and writable. And we can turn PPL code into executable code that can go and make whatever changes are necessary. Once that code finishes running, we can exit PPL mode and restore normal kernel mode in a way that's fully validated. The page protection layer, in short, gives us something pretty amazing. It gives us system-wide dynamic code integrity enforcement even under the assumption of a compromised kernel. And it provides a massive attack surface reduction for code signing validation and page table management. On top of that, it does this all with really low overhead. There are no hypervisor traps. There's no nested page tables. It's very, very fast because we were able to build this into our silicon. Now we're in a pretty good place about code integrity, both in kernel and in userland. But what about control flow? Last year, with iOS 12, we built support in iPhone XS for ARMv8.3 pointer authentication instructions. These are instructions that basically use spare bits and a pointer to store a cryptographic hash. And this mechanism is designed to be robust in the presence of even arbitrary read-write primitives. So let me give you an intuitive sense for how this works. There's a set of keys, and I'll explain more about them in a moment. One of them is selected for the write operation. A pointer is taken, optionally some extra data for diversification. That's all passed into an encryption function, which produces a signature, which we use to generate our signed pointer. So here's the premise. This is a real pointer. Really, if you look at it, it has an address and some padding. So a sign operation will go perform the signature, stuff the signature into the padding. A later authenticate operation will check whether that signature is correct. And if it is, it'll just zero it out, which will turn this pointer back into a valid pointer. If the signature check fails, instead of zeroing this out, we will leave the high bit set, which turns this into an invalid pointer. It's a pointer that the next time it's dereferenced will simply crash. We do this with 5 different keys: IA, IB, DA, and DB, and GA. The way to the cheat sheet here is I keys are instruction keys, D keys are data keys, and then A keys are generated randomly at boot versus B keys, which are generated anew every time a process is created. The reason that A keys are generated once at boot and then reused across processes is because iOS, being a mobile environment that is memory constrained, takes a strong set of performance optimizations in the form of DYLD shared cache and many other ways to basically map the same code into every userland process. And so if we insisted on not having any shared pointer authentication keys across different processes, we would be paying an unacceptable memory overhead of many megabytes just to have the system running. Ultimately, these keys, because they're backed by hardware, are not readable by an attacker regardless of the level of privilege. So what do we do with this? Well, we protect a number of types of pointers to code. Here you see for each one of these what kind of key is used, and then on the right-hand side you see what is used for diversification. Here's, again, an intuitive example. This is before pack. We have a function, prolog would normally store the link register on the stack. We would run the function. At the end, we would restore the link register, and we would return to it. With pack, we add this pair of instructions. The first of them, if you see in the upper right-hand corner, basically says, hey, take the link register, use the IB, this is the per process code key, and the storage address of this specific thing on the stack as a diversifier, sign that, so that when we're finished executing, a single instruction will both verify that the signature is correct and return to it. We don't just protect code with this. We also protect pointers to data and pointers to code via data. So these are some of the most important ones. We don't want an attacker to be able to redirect kernel code flow by waiting until an exception is being taken and kernel thread state is being spilled, and then simply overriding that kernel thread state. So to fix that, we sign and hash a number of items in the kernel thread state to prevent modification during an exception handler. The other one that's interesting here is C++ vtable pointers. We use PAC to protect both C++ vtable pointers and entries, which is interesting because it has an additional property over just control flow integrity. It's actually a very effective mitigation against use after free attacks on C++ objects. Not only can an attacker no longer fake a vtable pointer during exploitation of a use after free bug, but we actually record the intended prototype of a function and make sure during signature checking that the thing that we are actually going to jump to matches that prototype, which means that type confusion attacks are very, very difficult. We first shipped this with iPhone XS and iOS 12, but in iOS 13, we have been firing on all cylinders in getting broad adoption of PAC across different parts of the system. In iOS 13, authentication failures in PAC during kernel execution abort. They no longer just generate an invalid pointer that will later be dereferenced. They cause a full abort. We have adoption across every Apple text. We've hardened our jump tables. We've hardened our Objective-C message dispatch handling. We've hardened our exception handlers. And then JavaScript core, JIT, and extra data was used throughout to increase the protection level on JavaScript core as well. In a future software update to iOS 13, we are going to start also signing high-value data structures. Not code, not pointers, just data structures that are really high value to potential attackers. So that's everything from processes and tasks to code signing structure members, structures in the virtual memory subsystem, and certain IPC structures. Last but not least, I want to talk about Find My. This is a new feature that feels like a bit of practical magic. We want to help users be able to find their lost devices, even when those devices are offline. We want to make it the case that any device in proximity can help find a lost device, even if that device belongs to someone who's a complete stranger to the owner. So the way we want to do this is to have offline devices communicate via Bluetooth with any participating stranger, who might be a finder in this case. These finders would then report their location and the timestamp, and the owner would use their second device to find the lost device. Doing this in the straightforward way, the way it's been traditionally done, doesn't work. If you assigned a static identifier to a device that it kept broadcasting, you could just track that device anywhere it moves. And even if you rotated the identifier, the finder would not actually be able to encrypt location end-to-end, which means that whatever server was being contacted would actually have access to all of this location information. We had a much more rigorous set of security and privacy goals. We wanted to make sure that location reports are not accessible to Apple servers under any circumstances, that Apple servers can neither read nor modify nor even add bogus location reports. We also wanted to protect finders, both their identities and location, in a way that's never revealed to Apple servers. We wouldn't want to record any finder identities, and we'd want to make sure that any reported location is encrypted in a way that Apple servers cannot read. Lastly, we want to make sure that whatever data a device is broadcasting when lost cannot be used to track it, except by the owner. So how does this work? Each device undergoes a setup procedure. It generates an elliptic curve P224 key pair, as well as a symmetric key, and stores all of this in iCloud keychain, where every other device belonging to the same user can access them. The use of P224 is key here because it generates a 28-byte public key, which means we can just barely stuff it in the 32-byte packet limit for Bluetooth under version 5.0. When a device wants to broadcast its location, it figures out the current time period, which for us is 15 minutes long, and derives a symmetric key from the original symmetric key that is specific to this time period. The KDF that's used here is ANSI X963 with SHA-256, if you're curious. And the broadcasting device also derives an anti-tracking secret pair, which is in turn used to unlinkably diversify the original public key every 15 minutes. In other words, every 15 minutes, a new public key is generated that, even though it is clearly connected to the original public key, no one except the owner of that key pair can figure out that these are linked. Finally, it is this unlinkably diversified public key specific to this 15-minute time period that is broadcast to nearby finders. When a finder receives a broadcast like this, it does something called ECIES encryption to the public key that's being broadcast. The way to think about ECIES is it's non-interactive elliptic curve Diffie-Hellman to the key, as well as a symmetric key derivation, and finally an encryption to that symmetric key. In our case, that's with ASGCM. The finder also takes this public key that it received, it hashes it, which turns into a lookup index. And basically, the finder will turn around and tell the Apple service, hey, for this lookup index, store this encrypted data. When an owner then later tries to locate their lost device, what they will do, starting in the lower left-hand corner, is first, they will retrieve their original information from iCloud keychain. They will start going backwards in time in 15-minute intervals from right now, computing each diversified public key that was active for that device in that 15-minute time period. For each of those, it'll compute what lookup index that device would have been reported under. And finally, it'll query the Apple server database and say, hey, do you have a report for this index? If the answer is yes, the report comes back as an encrypted blob, which the owner can now ECIES decrypt to retrieve the location timeline of their lost device. I love this because it's a novel design and it enables something that feels powerful, which is to turn all of us into potential finders for lost devices, even though we don't know each other. But the privacy properties that are maintained here are exceptionally rigorous, both in terms of protection to device owners and finders and the devices themselves and their own trackability. So here's what we talked about. We built a world-class secure boot implementation for the Mac using the T2 security chip and deployed a series of novel industry-first protections like PCIe Buzz Zero, as well as the option around Sandbox, to significantly strengthen the secure boot process and deliver something that rises to the level of meeting our requirements. With iOS code integrity protection, we iterated on a series of approaches using our ability to build silicon and write software until we converged on a set of mechanisms that give us very strong protection for kernel code and data, userland code, and lastly, using Pointer Authentication, the ability to constrain control flow to exactly what is expected. Lastly, with Find My, we took something that felt like it should be possible, but for which traditional approaches were simply unacceptable to us from a privacy and security perspective. And we found a way to meet those strong requirements and make this something that we can make available to everyone. I'd like to share some news with you. In 2016, at Black Hat, we introduced the Apple Security Bounty. And what we did was very different than most bounties at the time. Instead of focusing on a wide variety of categories or trying to have many, many reports from many people, even if they are of low immediate impact, we said we're going to focus on only the most high impact categories of vulnerabilities. We're going to constrain our platforms to iOS and iCloud, and we will invite a very small number of exceptional researchers to participate in this bounty program. At the time, our maximum payout of $200,000 was the largest in the industry. This has worked really well for us. Even though we focused on only the most high-impact vulnerabilities and invited only a very small number of researchers, we received around 50 very high-value reports in these exceptionally critical categories. But we'd like to take this further. I'm happy to announce that the Apple Security Bounty will be open to all researchers in the fall. Thank you. And we're going to expand our platforms as well. From iCloud and iOS, we're adding tvOS, iPadOS, and watchOS. and Mac OS. We have completely revised and expanded our bounty categories. I'm not going to be showing you the whole list today, but I will highlight some of the most important ones. So this is our new list of top-level categories. The iCloud category remains effectively unchanged, but the device-side categories are now completely different. They focus on attack via physical access, attack via a user-installed app, a network attack that requires user interaction, and lastly, a network attack that requires no user interaction. For each of these subcategories, the maximum payout per subcategory will be $100,000 for iCloud, up to $100,000 for lock screen bypass, up to $250,000 for user data extraction via physical access, up to $100,000 for unauthorized access to high-value user data from a user-installed app, up to $150,000 for kernel code execution, and up to $250,000 for CPU side-channel attacks against current Apple silicon. For one-click unauthorized access to high-value user data, it'll be up to $150,000. For one-click kernel code execution, up to $250,000. And finally, in the hardest category of network attacks with no user interaction, a zero-click radio to kernel with physical proximity escalation is up to $250,000. And a zero-click access to high-value user data will be up to $500,000. We're going one step further. In certain pre-release builds, like beta releases that we make available to our developers, that we will designate, any vulnerabilities that are discovered in those pre-release builds which were not introduced prior and are reported to us before that operating system goes out to customers, we will offer a 50% bonus on top of all of those payouts. The second best reason to have a bug bounty is to find out about a vulnerability that is already in the user's hands and fix it quickly. But the number one best reason to have a bounty is to find a vulnerability before it ever hits a customer's hands. We also thought about what it's like to get started with vulnerability research on our platform. iOS chains are hard to come by. And we want to attract some of the exceptional researchers who have thus far been focusing their time on other platforms. Today, many of them tell us that they look at our platform and they want to do iOS research, but the bar is just too high. They would have to first have a full chain just to bootstrap their research. We also feel like existing iOS researchers should not have to hold back chains to be able to continue their research. So I'm proud today to announce the iOS Security Research Device Program. This is an unprecedented, fully Apple-supported iOS security research platform that comes with SSH, a root shell, and advanced debug capabilities right out of the box, using a new researcher fusing that's neither production nor development. While this program will be by application only, we will evaluate applications from anyone with a track record of high-quality system security research on any platform. This program is coming next year. The Apple Security Bounty has served us well, and we are excited to take it to the next stage. We will invite all of you to participate in the fall. We have a new, fully expanded and revised set of categories. We have by far the highest maximum payouts in the industry. And we have the iOS Security Research Device Program for exceptional researchers that are new to our platform. But we asked ourselves one last question. What if someone came to us with a zero-click iOS full chain with kernel code execution and persistence? I'm happy to announce that we would reward it with up to $1 million.